Enlarge a single atom to the size of a classroom, and its nucleus is roughly the size of a pinhead. Ernest Rutherford discovered this extreme scale over a century ago, proving that the vast majority of matter is entirely empty space. But if you travel across that void and plunge directly into the core, you hit a densely packed, violently trembling cluster. This tiny speck contains more than 99.9% of the atom's mass, divided into two types of particles, protons and neutrons. These particles have specific electrical properties. Protons carry a positive electrical charge, while neutrons, true to their name, carry no charge at all. And that simple fact presents a massive problem. According to the standard laws of physics, packing this many identical charges together in a microscopic space shouldn't be possible. We know from the basic rules of electromagnetism that opposite charges attract and like charges repel. Gravity tries to pull mass together, but the mass of a single proton is unimaginably small. The outward repulsive push of their electrical charge is astronomically stronger than the inward pull of their gravity. If electromagnetism and gravity were the only forces in the universe, the core of every atom would violently detonate. Yet the physical world around us clearly exists. That means there must be a third massive mechanism at play, a completely distinct fundamental force, strong enough to overpower electrical repulsion. Physicists call this the strong nuclear force. It acts as the ultimate cosmic glue, overriding everything else to bind protons and neutrons together. To function, this force relies on a strict set of rules. First, it operates at a magnitude entirely separate from the physical world, easily dominating the Coulomb force trying to tear the nucleus apart. Second, it completely ignores electrical charge. The nuclear force will pull a proton toward a proton with the exact same grip as it pulls a neutron toward a neutron, or a proton toward a neutron. Because it disregards both electric charge and the weakness of gravity, physicists realized they were mapping a mechanism with an entirely different mathematical framework than classical physics. This chart shows the potential energy between two nucleons based on the exact distance separating them. That distance is measured in femtometers, 1/quadrillionth of a meter. Look at the far right side. When the particles are separated by more than a few femtometers, the nuclear force effectively drops to zero. They have no influence on each other. But as they close the gap, the energy dives into a deep well, hitting maximum attraction at exactly 0.8 femtometers. This creates the overwhelming inward pull needed to defeat the electrical repulsion. If they get any closer than that, the graph spikes vertically into positive energy territory. The force abruptly reverses, becoming intensely repulsive. The nuclear force is a highly calibrated spatial trap. It pulls matter together tightly enough to forge an atom, but pushes back at point-blank range to stop those particles from collapsing completely. Because this force falls to zero outside of a tiny, specific window, a proton or neutron can only interact with the particles immediately touching it. This creates a property known as saturation. A nuclei maxes out its binding capacity with its closest neighbors. Adding more particles to the outer edge of a large nucleus does not increase the grip on the particles trapped in the center. Meanwhile, the electrical repulsion has a much longer reach. Every single proton in the nucleus is constantly pushing against every other proton, regardless of how far apart they sit. Because the nuclear grip eventually saturates while electrical repulsion scales up, the average binding energy holding each particle in place naturally levels off. This graph shows that exact plateau. For the massive chunk of elements in the middle of the periodic table, the binding energy per nucleon stays nearly constant, hovering around 8 mega-electron-volts. That flat region is the structural foundation of the matter we interact with daily. The energy holding it together is millions of times denser than the energy generated by conventional chemical reactions. We can calculate the exact scale of that energy using Albert Einstein's mass-energy equivalence. The nucleus physically weighs less than the sum of its individual parts, with that missing mass converted directly into this binding energy. Our physical reality survives on these precise microscopic margins. If the nuclear force reached any further, elements would collapse. If it were any weaker, atomic structure would shatter. Instead, it balances exactly where it must.